Okay, thank you, Paulo, and thank you to be here after the lunch to see this talk. I'm very glad to be here and have the opportunity to show more details about the method that we have recently developed to study phase transitions. And I'm sorry, I didn't see there is a misspelled on the use of the energy probability distribution zeros in the study of phase transitions. And this work was done in collaboration with Bismarck and Júlio Rocha. Júlio is now at Ouro Preto. And also Ronaldo and Rodrigo, two students of our group that also made some contributions to some results that I will show you today. This is a brief outline of my talk. I will do a brief review of something about what Bismarck said this morning, in the case if some of you were not here. Then I will apply the model, our methodology to the Ising model, Potts model, XY model. And then I will also go back to the Ising model to show you some problems that we already identified in this procedure, and perhaps think about some ways to solve these issues. And finally, my closing remarks. Okay, so the entire idea of this method is based on the Fisher zeros, or the zeros of the partition function. Then if you have a system with discrete energy levels, you can write the partition function of the system as a polynomial, okay? And if you have a system with continuous energy levels, you also can discretize these energy levels. So the idea is pretty much the same that we will use here. Of course, the size of the bins that you use to discretize energy, they may have some effect on the system, okay? But you can choose different bin sizes to do that, so there's no problem. So we have here, if you have m different energy levels, you have m complex roots for this polynomial, and the number of states here are positive real numbers, so that these roots appears as conjugated pairs, and there is no positive real zero for the partition function. It's a positive number, okay? But in the thermodynamic limit, we should expect the existence of a real zero of the partition function, reflecting the fact that the free energy of the system is non-analytic. Okay, so the free energy is given by the logarithm of the partition function, so that when it's zero, you have a non-analytic behavior there. And we do expect that at least, so if you have a system that there is a phase transition in it, we should expect at least one of those roots to approach the real axis in the thermodynamic limit, okay? So if you take the size of the system going to infinity, the imaginary part of the zero goes to zero, okay, while the real part is finite and is directly related to the critical temperature of the system. And this zero that touches the real axis in the thermodynamic limit, we called it leading zero or dominant zero, okay? But we do have some problems with this approach, because you need the full density of states to calculate the zeros, okay? But it's hard to obtain. And but perhaps the main problem here is, for example, if you take the 96 by 96 Ising model in a square lattice, you have 10 to 2,700 orders of magnitude in the coefficients of the polynomial. So it's very unlikely that you have any reliable numerical method to find all these roots. And because of the great order of magnitudes that you have here, and in addition to that, you have about 10,000 roots for this polynomial. You have a polynomial of degree about 10,000 and coefficients that it spans over thousands orders of magnitude. So it's a very hard numerical problem to solve. And you have no clear criteria to among all these coefficients, select those that are most important for a phase transition. So the method that Bismarck showed you today is indeed a way that you can filter the most relevant coefficients for this problem. So the idea is that you multiply here by 1 and write a new polynomial. Now the coefficients of this polynomial are the unnormalized energy probability distribution, and you are writing it in a new variable x that depends on the difference between the temperature beta and beta naught, that is a reference temperature that we are using in this approach, okay? So if you have a phase transition at exactly if you make beta naught equals to critical beta, you have x equal to 1, and since it's a phase transition point, the partition function should be 0 at this point, at the thermodynamic limit. So we have a way to, if you look for the distance between the dominant 0 and the point 1, 0 in the map, we have a way to estimate the critical temperature related to the critical temperature of the system, even you are not exactly at the critical temperature, okay? So if we are close enough to the critical temperature, we know that states that have a very low probability to occur will not play a significant role in the system properties. So we can simply throw them away and take on the states with relevant values of the heat to be considered. So now we know that when we are close to the critical temperature, we can safely filter and diminish a lot the size of polynomials that we are working with. In addition, we can also control the range of coefficients in this polynomial. So we are changing a little bit the things, but we still keep valuable information here, as will be clear in some moments, okay? So the algorithm that we propose is that you have a system, you start with a temperature that you like, build the histogram at this temperature, then you cut this histogram taking the most relevant energy states for that temperature, okay? Find the zeros of this polynomial, and then you find the dominant 0 in general, the 0 that approaches the most the real axis, okay? And if it's close enough to the point 1, 0, okay, you are at the critical temperature, but otherwise you can make another estimate of the critical temperature using the distance between this dominant 0 and the point 1, 0, okay? So let us detail this a little bit. I will use first here the fruit fly model of the statistical mechanics to the Ising model in a square lattice. So I have spins that point up or down. There is a second order phase transitions, a temperature that is known exactly, okay? We also have exact results for the density of states for the system. For size, we could calculate it up to 96 by 96 lattice size, okay? So here I will use the exact results for the density of states to build histograms, and then I will cut the histograms to calculate zeros, okay? And the only values of the histogram, the process here is the following. I will set the maximum value of the histogram to 1. And all values smaller than 10 to minus 2, I will throw them away. Okay, so I will have coefficients that spans over 2 orders of magnitude instead of 2,000 orders of magnitude. Okay, and consequently, much smaller polynomial degree. Okay, just to show you the main problem that we have with this zeros finder task. Consider, for example, a 16 by 16 lattice at the temperature beta equals to 0.44. Then you have here the histogram of energies. Okay, all the energy range is plotted here, but of course for these values of energy, the probability is too low, and it approaches 0. And if I try to calculate the zeros of this polynomial, I get the result that is shown in this plot. In black, I made no cutoffs. I mean, I'm just rescaling the Fisher zeros. If you look here, what we have done is just multiply the Fisher zeros. We have e to the minus beta epsilon. Okay? In our zeros, we are multiplying it by epsilon to the beta naught epsilon. It's just a rescaling of Fisher zeros, okay? So they are essentially the same zeros, but rescaled now. And so by doing a simple rescaling, I have the Fisher zeros for the 2D Ising model, okay? But as you can see here, I did this in Mathematica, and it shows a lot of roots at the real positive x, where I know that can be no root. This is a numerical problem when you deal with such a high polynomials with a very great range of coefficients. Then if I reduce it, now I will throw away values of the histogram that are smaller than 10 to the minus 46. I get those points in red. I will make a zoom in this region. And if you see, they agree for all these points. Some of the roots that were on the real x simply disappeared, but I still have zeros here, so the zeros finder isn't working properly yet. I still have numerical problems here, okay? But it seems that some of those zeros were found correctly, at least. It seems to us. If I do now my cut at 10 to the minus 10, all this region remains the same, but now I have a more well-behaved polynomial that I can trust much more than before. Now I have a smaller polynomial with a smaller coefficients range. And if I go further and cut at 10 to the minus 2, if you see this 0, that is the one that I believe is the dominant 0 for that indicates the presence of a phase transition to the Ising model, it remains almost exactly at the same position. All other zeros were modified, but this one seems to be pretty stable and is when we believe that it should be. Okay? So using these exact values of the density states, cutting in 10 to minus 2, this is the same table that Bismarck showed this morning. We start, for example, at temperature equals to 3, iterate the algorithm, and then we will end up with this temperature that the criteria that we use to stop is how close the real part of the 0 is to 1. Okay? So here we have 4 figures. And And then we can proceed to the other lattice sizes, and then after just one iteration, you get a value that we judge that is close enough to 1, and you proceed for all lattice sizes, and then you can use conventional finite size scaling theory to extrapolate this value to the thermodynamic limit, and you obtain a value that is very close to the exact value. See, we are using lattice size from 4 to 96 for the Ising model are pretty small lattice sizes. We are using a cutoff in the histogram at 10 to the minus 2. Okay? But even this way, it gets errors smaller than 0.5%. If we go further, we can see that we do expect that the pseudo-critical temperature follow this power law from finite size scaling theory. But the real part of the dominant 0 is equal to 1 for all lattice sizes. So if you look only to the imaginary part of the dominant 0, you should expect that it follows the same power law. So if you take the logarithm of the imaginary part of the dominant 0 as a function of the logarithm of the lattice size, you see a nice power law. L equal to 4 is too small, so we didn't consider it in this fit, but we get 1 over nu equal to 1.006, which is very near the exact value 1. So using this approach, we get the critical temperature and a nice estimative for the exponent nu at the same time. Okay, now let's move on. Try it in other models, in other situations. The 2D Potts model with Q states, with neighboring spins are in the same state. You count 1 in the energy. If not, they don't interact. It has second order transition for Q smaller or equal to 4. And first order transition for Q is greater than 4. The critical temperature and exponents for this model are known exactly. And in this case, we used conventional Monte Carlo simulations with Metropolis algorithm. Okay, no secrets here. The idea was to see, let's try the basic things, the most crude implementation. Let's see if the model works in the worst situations somehow. We know that there are many sampling techniques that could be used here, but let's try first with the basic. Okay. The cutoff now was in 10 to the minus 3. Okay. So I will detail the process here. We start, I did a simulation at t equals to 2. Build the histogram. Here is the complete map of zeros. Then I choose as the dominant 0 the one that is nearest to the point 1, 0. Okay? Then I take this guy, and the real part is given here. Okay? Using the distance to the point 1, 0, I can obtain the my first estimate for the critical temperature, that is about 1.5. Then I get the histogram, the zeros, and the real part of the zeros. Then you can proceed with this process, building histograms, new map of zeros, and new real parts. Then eventually it starts to approach 1. Okay? So here I have used, this is for 20 by 20 lattice, 10 to 5 Monte Carlo steps. Okay? And if you proceed here, you see that it starts to converge. And after 7 iterations, I have a relatively nice convergence. Okay? So the idea of the approach is take a small system size, run a small simulation that is very very fast, and you get your first estimate. Then you can proceed to larger lattice size, better sampling of your system, and so on. Okay, so here I'm showing the same convergence. Before, this curve here is the same that I just showed you, but together with attempts that we will start at different temperatures, just to show you that it always converges to the same value, as we should expect. Okay, in red here is for for the 6 states POTS model, and in blue is for the 10 states POTS model in a 20 by 20 lattice. Okay, so we can see that it converges pretty fast in this case. There is a point that we should note here. When you have second order phase transitions, okay, you just throw away the tails of your distribution. But if you don't have much care when dealing with first order transitions, you may have the risk that throw away very important informations that are here. So the approach is you came from low energies and high energies, and the first time it goes above the limit that you decide to use for to cut your histogram, then you have the energy range that have to be used. That is the entire range between these values. Okay, so you cannot throw away this value here, since you would have a big problem here. Okay. So here, just to show you, for the 3-state spots model, we have run 5 different simulations with each of one with 10 to 6 Monte Carlo steps. Okay, here are the temperatures that run, and we use histogram reweighting here instead of to iterate the algorithm, because we choose temperatures that are close enough to the critical temperature for that lattice size. Using this approach, and 2 or 3 iterations depending on the details of each lattice size, we see that the log-log plot of the imaginary part of the zeros give this really nice straight line with an exponent 1 over nu equals to 1.19, while the exact value is 1.2, lattice size between 20 and 160. And for the critical temperature using finite size scale, we get this value that is, again, pretty close the exact value here. For the Q equal, here we have a second order phase transition, okay? For Q equals to 6, we have a first order phase transition. We use the same approach, but of course here, since you have 2 peaks in your energy probability distribution, you have to have much care with your simulations. So we use different temperatures here and multiple histogram reweighting to use our algorithm, okay? So we get estimates for the critical temperature and the imaginary part of the zeros that, again, follow the expected power law. In this case, we do expect that it scales with the system volume. Okay, and in red here we have a linear fit, but in this case we saw that corrections to scaling was in order to get more precise results. So the first correction to scaling here is one that depends on the volume squared. Okay, so here is a fit to a parabola for both of them. The points are very well fitted by this function, and we get, using this approach, a very nice value for the critical temperature for the system. Just another playing with those things. In the 10-state spots model, very small lattice sizes. Remember, I'm using Metropolis. Here we have a very strong first-order phase transition. Then, using only Metropolis, and for such a very small lattice size, we already see clear signs that it is a first-order phase transition. And surprisingly, in my opinion, for such small systems, such somehow crude simulations on 10 to 6 Monte Carlo steps, okay, we get a very nice value for the critical temperature. I should remark that in all these figures that I showed you, the error bars that I took among 5 different simulations for each temperature are included here, okay, and are smaller than the symbol size. Okay. Other example that we have studied is the 2D XY model that has a Kosterlitz-Taulis transition. The free energy is C infinity, and we have a line of critical points below the transition temperature that is around 0.7. Okay. For this study, we used the density of states obtained by using the radical exchange Wang-Landau algorithm, okay, to build histograms and use this approach. Here I can show you the map of zeros for some temperature. We are interested in try to study a little more the fact that in this case, you see, there is an almost flat region here of zeros that we have some suspicions that it may be related to the fact that you have an entire line of critical points at low temperatures in the system. But if you choose only the zero that is nearest to the point 10, okay, we can obtain the transition temperature. In this case, the arrows here came from 5 different density of states, consequently 5 different histograms and maps of 0. So we have the errors, and they extrapolate to the predicted value. For the 2D XY model, the scaling is expected to be with the logarithm of the lattice size to the power -2. Okay? So, everything is okay up to here, but we still have found some problems. The problem that we found was mainly Ronaldo have obtained this result. He started to study to the Metropolis algorithm and Monte Carlo simulations and multiple histogram reweighting for L150 and 10 to the 8 Monte Carlo steps at each simulation. Okay, what we have seen that depending on the chosen threshold that you use in your histogram, you may have or may have not convergence of the algorithm. So if you cut at 10 to the -1, you see it converges to a nice value of temperature here. If you use 10 to the -4, it converges almost instantaneously. But for some reason, at 10 to the -2, you start at this temperature, it sends to this, and then you have this strange shape here. Perhaps the plan. Here we have three. My spin has the Z component, that one that will go to the temperature. I mean, the planar rotator model. It's quite a different model here. We have 1 degree of freedom more, and then the temperature is slightly lower. Okay? So this lack of convergence, we don't know exactly where this came from. I mean, this is the same data set, the same histogram that was used to get to this result. Okay, so we're trying to understand this a little better. We decide to do a scan over a large range of temperatures. So you start at high temperatures, choose a small step on it, okay, and calculate it. And here I'm showing the path that the dominant zero follows in the complex plane in this case, okay? So when you look for 10 to the minus 1, it follows this path, and here you have the critical temperature when the real part of the zero is equal to 1. So starting from high temperatures to low temperatures, the dominant zero follows this path in the map, in the complex plane. Here for 10 to the minus 4, you have a well-behaved path. But when you, for the cutoff where it doesn't converge, we see that it seems to try to approach the point 1 here, the point where the real part is equal to 1. It came here, but it started to go up, and then it jumped for these 2 or 3 points here, and then jump back for here and go on. So it seems that for some reason it's avoiding the point 1, 0, and we are not sure about what is causing this. So let's take some representative points of these graphs here. So any map that you take on this curve will be very similar to each other. If you look with much care to this region here, we can see that you have 3 zeros, and the 0 at the middle are a little bit lower than the other ones. Okay? If you take a point near here, you see that instead of the 0 of the middle, the 0 on the right is a little below. And if you take here, on the other side, the other 0 is below. We suspect that some small fluctuation in the histogram is causing this behavior. It's strange because, okay, I said to Ronald, try to run another simulation, take another histogram, and the same will happen. So there is something strange. Perhaps the polynomial here is still large. Okay, we have how much roots do you remember? I mean, the degree is I'm pretty sure it's about 1,000 or so. Okay, so we have still a very big polynomial here. That we get was 96 by 96. Yeah. But, I mean, we have simulations for a lot of lattice size and a lot of different cutoffs, and this happened for just a very few of them. And in this case, I mean, we don't have many ways to predict when it will happen or not. Yeah, I mean, I can say you that for Fisher zero, I don't. If you take lattice size above 8 by 8, okay, the results that Mathematica show you are not correct. Either you have zeros on the real axis, or you don't have conjugated pairs for all zeros. So I know for sure that Mathematica is making some mistake at some point. Okay, But for such a small system and the Fisher zero. Okay, and if you take those few points that you have here, it is choosing the zero that is in the middle, but it seems for, at least I believe that the imaginary part here is being overestimated. I would expect a smaller value perhaps around this region here instead of up here. So it seems that in this case there is a problem or with the polynomial or with the roots finder. Okay? We are not sure about what is really happening. And we see very similar behavior in a completely different system. Here I'm showing a problem that I work very much with it, that are spin-ice-like systems. We have a network, a lattice, of elongated nanomagnetic islands. Okay? So each arrow in this figure represents a nano island about 200 nanometers long, okay, that have a magnetic moment that is restricted to point along the long axis of this nano island. So essentially it's like Ising spins, okay, but the interaction among them is dipole-dipole interactions, okay? So in this special geometry, we do expected excitations here that behave like magnetic monopoles that are restricted to move only along one line. So we had some suspicions that may have some effects from dimensional reduction in the system. That's why we start to study it. And I proposed, Rodrigo, let's try to use the zeros for this problem. And what he did find, that for some values of that he chose, it doesn't converge at all. Okay, so it's very similar to what happens for the XY model. Okay, and I'm starting to study even another system that seems to have the same problem. And our main suspicions right now is that it have to do with some small fluctuations and the polynomial. It depends where you start and then to where it will converge. When it but in the Ising case, I would not expect that. Yeah. Then we are now perhaps the best idea that we have now. Bismarck has shown this morning that you can change the way that you define the zeros. Instead of it converts to the point 1, 0, it converts to the 0, 0, and then you can make a Hay scale and have yet the dominant 0, but avoiding again problems with polynomial. So we'll start to try this approach here to see if it solves this problem, okay? And here, just to show you again, for this spin-ice model, when you do a scan temperatures again, when it converges, you see a well-behaved path that passes by the point 1, and when it doesn't converge, it seems to avoid. These are very small temperature steps, and then it goes here, 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 and then jump direct to this point, and here, here. Again, the idea here is that if you look for the map of zeros, you see that it jumps from this 0 to this 0. So it's choosing the zeros at the border, but these at the sides instead of the what I would expect to be the 0 at the middle. Yeah, yeah, yeah. Yeah. Okay. So my closing remarks, we have shown that the energy probability distribution zeros is a good quantity to study phase transitions. It can be applied to essentially any model once you can get the ADP, gives accurate estimates for temperature and the critical exponent nu, works for first, second, and BKT transitions, is less susceptible than the Fisher zeros to problems related to zeros finder task. The energy probability distribution is in many systems easier to obtain than the density of states, and you don't have here ambiguities related to which quantity you are looking for. Okay, and of course we have to do a lot of work to completely understand this, especially these features related to the convergence of the algorithm and so on. Okay, so thank you.